Fusion Mobile, quality e-learning experience on the go.
Computer data conversion. A bus is a communication system that transfers data between components inside a computer or between computers. This expression covers all related hardware components. Just like a bus takes you from your house to the town or from your house to a friend's house, this is just the same way a bus in a computer takes information and data from one point to another. It can come in different ways in the form of wire or optical fiber, and it comprises the hardware and the software, including the communication protocols. Early computer buses were parallel electrical wires with multiple connections, but the term is now used for any physical arrangement that provides the same logical function as a parallel electrical bus. Let's now define some concepts with computers. We see first of all the memory address. The memory address is a number that is assigned to each byte in a computer's memory that the CPU uses to track where data and instructions are stored in RAM. Each byte is assigned a memory address whether or not it is being used to store data. The computer's CPU uses the address bus to communicate with memory address it wants to access, and memory controller reads the address and then puts the data stored in that memory address back onto the address bus for the CPU to use. Let's talk about the register. The register is just a small amount of storage available as part of the central processing unit. Such registers are typically addressed by mechanisms other than memory and can be accessed faster. Almost all computers load data from a larger memory into registers where it is used for arithmetic, manipulated or tested by machine instructions. Let's understand this way. The computer has its main memory, but sometimes it just wants to do a very fast calculation of 1 plus 1. Before it activates the main memory and gets to it to store things, it will take a long time. That is why it uses the registry to store 1, the operand plus, and the other operation 1, and then it gets the result 2 very much faster. Manipulated data is then often stored back into memory, either by the same instruction or a subsequent one. Registers are used to quickly accept, store, and transfer data and instructions that are being used immediately by the CPU. Let's now talk about a processor. A processor often contains several kinds of registers that can be classified according to their contents or instructions that operate on them. Let's take an example, the user accessible registers. Instructions that can be read or written by machine instructions are called user accessible registers. The most common division of user accessible registers, or UAR, is into data registers and address registers. What are these? Well, data registers can hold numeric values such as integers and, in some architectures, floating point values. When we say floating point values, we mean values that have decimal places, as well as characters, small bit arrays, and other data. In some older and low-end CPUs, a special data register known as the accumulator is used implicitly for many operations. Address registers also hold addresses and are used by instructions that indirectly access primary memory. Special purpose registers called SPRs hold program states. They usually include the program counter, also called the instruction pointer, and the status reporter. Let us now look at internal registers and other registers. Internal registers are not accessible by instructions and are used internally for processor operations, while instruction registers are those ones that hold the instruction currently being executed. Registers related to fetching information from RAM or other CPU operations are the MBR, which is the memory buffer registry, the MDR, which is the memory data registry, and the MAR, which is the memory address registry. Hardware registers are also similar to this, but they occur outside the CPU. Now let's now understand this. An instruction cycle. An instruction cycle, also called a fetch and execute cycle or fetch decode execute cycle, that is FDX. Fetch decode execute, FDX, is the basic operation cycle of a computer. It is the process by which a computer retrieves a program instruction from its memory. It determines what actions that the instruction requires and carries out those actions immediately. This cycle is repeated continuously by the central processing unit from boot up to when the computer is shut down. That is, it fetch, it decodes, it executes. Again, it fetch, decodes, executes. In simpler CPUs, the instruction cycle is executed sequentially, one by one. Each instruction is completely processed before the next one is started. in most modern CPUs, the instruction cycle is instead executed concurrently in parallel or as an instruction pipeline. The next instruction starts being processed before the previous instruction is finished, which is possible because the cycle is broken up into separate steps. For example, as it's fetching one, it's executing another and it's decoding another. Let's now understand circuits that are using FDX. In FDX, a program counter, also called a PC, is used. This is an incrementing counter that keeps track of the memory address of the instruction that is to be executed next, or in other words, holds the address of the instruction to be executed next. We also have the MAR, as it said before, it means the memory address register. This holds the address of a memory block to be read from or written to. We also have the MDR, the memory data register, which is a two-way register that holds data fetched from memory and ready for the CPU to process, and also data waiting to be stored in memory. This is also known as the memory buffer register, or MBR. We also have the instruction register, which is a temporary holding ground for the instructions that have just been fetched from memory. We also have the control unit, which decodes the program instruction in the IR, that is the instruction register, selecting machine resources such as the data resource register, and a particular arithmetic operation, and coordinates activation of those resources. We now have the arithmetic logic unit, the ALU. This performs mathematical and logical operations. Arithmetic, mathematical, logical operations. We now want to look at the steps in FDX. That is the fetching, the decoding, and the effecting. That is the executing of the address. Each computer CPU can have different cycles based on different instruction sets, but will be similar to the following FDX cycle. First, it fetches the instruction. This instruction is fetched from the memory address that is currently stored in the program counter and stored in the instruction register. At the end of the fetch operation, the PC points to the next instruction that will be read at the next cycle. The decode instruction. During this cycle, the encoded instruction presented in the IR is now interpreted by the decoder. After that, it now goes on to effect or execute the instruction. In case of a memory instruction, the execution phase will be in the next clock pulse. If the instruction has an indirect address, the effective address is read from memory, and any required data is fetched from memory to be processed and then placed into data registers. If the instruction is direct, nothing is done at this clock pulse. But if this is an IO, meaning input-output instruction or register instruction, the operation is performed at clock pulse. We now want to understand the fetch, decode, and execute cycle. When it executes the instruction, the control unit of the CPU passes the decoded information as a sequence of control signals to the relevant function units of the CPU to perform the actions required by the instruction, such as reading values from registers, passing them to the ALU to perform mathematical or logical functions on them, and then writing the result back to the register. If the ALU is involved, it sends a condition signal back to the CU. The result generated by the operation is stored in the memory or sent to an output device. The cycle is then repeated. As you can see in this picture, we see the fetch. Here, we now see after fetching, it now goes over to what? Decode, and then executes, and then again it fetches. Let's now talk about factors that affect the speed of data transfer. When people talk about computer power, they usually mean the speed with which the computer processes data. Now, the circuitry design of a CPU determines the basic speed of a computer. It can be 286, it can be 386 or 486. It can either be Pentium 1, Pentium 2, Pentium 3, Pentium 4, and as we have today, Pentium M, dual core, and others. Other factors that affect processing speed include the registers. The size of the register, whether it's a high-speed memory location, or its word size, that is the amount of data that the computer can work with at any given time, will affect processing speed. When the size of the register is larger, the computer can quickly access processes more. That is why a system that is 64-bit processor can work faster than a 32-bit processor. Also, the memory and computing power of a system can affect its speed. When there is more RAM, this can increase the power of a computer by allowing the computer to use bigger and more powerful programs, and those programs can access larger data files. The amount of RAM can make a computer run faster, as increased RAM will allow the computer to fit more of the program into its memory. The data bus also affects it. The electrical part that connects the CPU, the memory, and other hardware devices on the system board is called a data bus. The wider the bus, the faster the computer can move data. Imagine that you're trying to transfer a group of school children from one place to another. If you have a larger school bus, more students can enter it, and that means that transferring them to and fro will be faster. That is how the data bus works. The address bus also works in the same way. It connects the CPU and RAM and carries the memory addresses. The wider the address bus, the more memory the computer can use.